Hello friends, welcome to my YouTube channel. Friends, today we are going to discuss the design procedure of the clamp coupling or split muff coupling. This is the basic diagram of the clamp coupling or split muff coupling. In this diagram, this is the input shaft and this input shaft is transferring power to the output shaft by the use of this split muff. The muff is being connected to the ends of the input shaft and output shaft with the helps of the bolts. These are the bolts. Okay, so we will discuss the design process in simple way. So the first step is the material selection for shaft, for key and for the sleeve. Generally, plain carbon steel is selected as the material for shaft and key, and the grey cast iron is selected as the material for the sleeve. Suppose I am selecting the material for the shaft as 40C8 plain carbon steel. Okay, so the material of the shaft being selected is 40C8 plain carbon steel, and for the key I am selecting the material as 30C8. Okay, and for sleeve the grey cast iron FG200 can be selected as the material for the sleeve. Now you have to note down from your data book the value of the yield strength in tension for the shaft material and for the key material and for the sleeve material. The ultimate tensile strength for sleeve material. Suppose for 40C8 the yield strength in tension is 380 Newton per mm square, which is being selected from the design data book, and for the key material 30C8 the yield strength in tension is suppose 400 Newton per mm square. Okay, and for the sleeve material the ultimate tensile strength is taken from the design data book as SUT is equal to 200 Newton per mm square. Okay, so this is the SYT. Yield strength in tension is denoted by SYT, and this is the SYT for the key material. Now the second step is the permissible stresses calculation. So we have to calculate the permissible shear stress for the shaft material, because shaft is subjected to the shear stress, torsional shear stress. So the permissible value of shear stress for shaft material is equal to 0.5 time into yield strength in tension for shaft material divided by factor of safety. Here we can take the factor of safety as 4 for safety purpose. So we can calculate the value of shear stress, permissible shear stress for shaft material by substituting the value of SYT, that is the yield strength in tension, using the shaft material. As I have taken the shaft material as 40C8, and for 40C8 380 is the yield strength in tension. So we can find out the permissible shear stress for the shaft material by putting the value of 380 in place of SYT here and factor of safety as 4. Similarly, we can do this for key, that is the permissible shear stress for key can be find out using the material for the key. The material of the key is 30C8 selected by us, so we can put 400 Newton per mm square here in place of SYT, and factor of safety can be taken as 4. Similarly, we can find out the shear stress, permissible shear stress for sleeve material and permissible crushing stress for the key material, okay, by using the data which we have taken for the material of the shaft, key and sleeve. So we can find out the permissible shear stress. Okay, now the next step is the diameter of the shaft calculation. In this step we will calculate the diameter of the shaft using these two formula. Generally in question the RPM of the shaft is given to us and the power being transmitted is also given to us. Suppose the RPM is given to us in the question is N is equal to 130 RPM. Okay, and the torque being transmitted is given to us as 50 kilowatt. Then we can put the value of the N and T from the given data which is given in the problem, and we can find out the power, this T is here, P is the power is given to us 50 kilowatt. So we can put the value of P here and put the value of N here, and we can find out the torque which is being transmitted, because power and N is generally given to us. So we can find out torque from here from this equation, and put the value of this torque from this equation into this equation. For the shaft material, the value of the shear stress that is being induced because of this torque is given by this formula, and using the torque obtained from this formula, we can find out the value of the diameter using the value of tau s as T shaft at the permissible shear stress for the shaft. In this formula, putting this value of tau s is equal to tau shaft, we can find the value of the diameter of the shaft. So the third step is completed, that is the calculation of the diameter of the shaft, and in the next step we will find out the dimension of the sleeve. Now the dimension of the sleeve can be taken as D is the outer diameter of the sleeve, this is the outer diameter of the sleeve D, okay, and it can be calculated as 2.5 D, where D is the diameter of the shaft as calculated in the step number 3, and the length of the sleeve can be calculated as 3.5 times D, that is where D is the diameter of the shaft calculated in the step number 3. So we can find out the dimension of the sleeve. Now the next step is the calculation of the dimension of the key. So the dimension of the key can be calculated using the diameter of the shaft as calculated from the step number 3. So we have obtained the value of the diameter of the shaft from step number 3, and using that value we will go into data book and look for the dimension for the shunt key, okay, shunt key, and for that we can see that corresponding to the various range of diameter, the key size is given to us in the design data book, that is the width of the key, height of the key, and depth of the key can be calculated corresponding to the diameter of the shaft. Suppose our diameter as calculated from the step number 3 is 11 mm. So if the 11 mm diameter lies in this range, so the dimension of the key will be 4 into 4 into 2.5. That is 4 is the width of the key, 4 is the height of the key, and 2.5 is the depth of the key. And length of the key is calculated using the empirical relation, which is equal to, that is the length of the key, suppose is LK is equal to 1.5 into D, where D is the diameter of shaft as calculated from the step number 3. Okay, so we can calculate the length of the key. So all the dimension of the key can be calculated, width, height, depth of the key, and length of the key can be calculated from this empirical relation. Now we will go to the step number 6. In step number 6 we have to find out the diameter of the clamping bolts. So the diameter of the clamping bolt can be found out using the empirical relations given in all data books. So you have to go into your data book and search for all these relations for the dimension of the clamping bolt given in the data book corresponding to the clamp coupling or split muff coupling. So if the diameter of the shaft as calculated from the step number 3 is coming out to be smaller than 55 mm, then you can use this formula to find out the diameter of the clamping bolt, where D1 is the diameter of the clamping bolt, by putting this value of D, that is the diameter of the shaft, as calculated from the step number 3. And similarly, if the diameter of the shaft is coming up to be greater than 55 mm, then you have to use this empirical relation to find out the diameter of the clamping bolt. Okay, so where D1 is the diameter of the clamping bolt, diameter of clamping bolt. Now the last step is the check for the key failure. Now we know that the key fail in crushing and in shear. So using this formula we can calculate the shear stress being induced in the key and crushing stress being induced in the key, where T is the torque being transmitted and D is the depth of the key. This is dt is the depth of the key, and B is the width of the key, and L is the length of the key. The dimension of the key we have already calculated in the step number 5, so you can put that from this dimension of the key. You can put the value of dBH in this formula and you can get the value of tau k, and similarly you will get the value of sigma c by putting the D, T, H and L, where L is the length of the key, H is the height of the key, and dt is the depth of the key, and T is the torque being transmitted by the key. So you can calculate the crushing strength of the crushing stress being induced in the key and shear stress being induced in the key by using these two formula, and from these two formula you have to compare the value of tau k and sigma c. This is the tau k and sigma c, that is tau k is this tau k and sigma c is this sigma k. So you have to compare these two values with these two values. If tau k is coming out to be, if this tau k is coming out to be smaller than tau k as calculated in the earlier case, then we can say that the key is safe in shear failure. And if this sigma c key, if this sigma ck is coming out to be smaller than sigma c key, permissible stresses for the key, then we can say that the design is safe. So this was all for today's video, and friend, if you like my video, you can subscribe to my channel and also press the bell icon for the notification of the upcoming videos. Thank you friend for watching the video.